With our second speaker, I have a rare opportunity to introduce fellow Nokian and fellow architect. Kamil Witecki is an experienced architect and chief engineer, master of many programming languages. You see, architect's work requires razor-sharp focus, but Kamil has so many hobbies and interests that he allows himself in his private time to be unfocused because he hardly can focus on anything. Today his talk is titled "Should I Care About CPU Cache?" Please give him a warm welcome.
Thank you very much for the applause. Thank you very much, Maciej, for introducing me. Yes, I'm Kamil Witecki, and I would like to talk about CPU caches. The talk will take around 45 minutes, and we will have Q&A session at the end. So in case you have questions, we will have time for that. Do not bother asking during the presentation. We'll have quality time just for the answers. The presentation will be on quite high level. It will be an overview. If after the presentation you feel that you would like to go a little bit deeper, you are in the right room, just stay here. Next lectures in this room will get you deeper and deeper in the topic and CPU caches and hardware optimization. All the opinions I am expressing here are my own, and the presentation was not endorsed by Nokia or any other person or company. What I would like to introduce you to is that caches are here to counter the latency in the system. They cannot remove latency, but they can make it relatively smaller. Another important thing is the organization of the caches. We can think that there is some cache and it's free lunch, but it's not true. Cache is there to help us, but we must take into account its organization so that we can actually make efficient use out of it. It will help us if we don't care about it. If we care about it, it will shine. And last but not least is the profits the cache can deliver us. It's not enough that we'll focus only on an algorithm. It's not enough that we'll have good data structures. It's not enough that we'll take care about the CPU caches. We must take care about the whole picture. At first of all, the relative latency. If we are thinking about computer, if we are thinking about modern PC, we have DRAM. And over the years, the speed of DRAM was increased tremendously. We can see that we are going from the level of hundreds of megatransactions per second to thousands of them. During the same time, latency didn't drop significantly. At the beginning it dropped twice, but later on the line stays more or less flat. So we are very good at pushing more data through the bus, but it takes more or less the same time between we ask for data and we receive it. It's similar, if we talk about bandwidth and latency, to moving a lot of data from one place to another. I could have hired a truck, fill it full of hard drives, and ask the driver go from place A to place B. Even if it takes 1 hour, the throughput will be tremendous because the hard drives are so densely packed with information. But when I'm talking about low latency, this would be terrible. It takes 1 hour to move that information and it will never arrive before that. When it comes to latency, simple child play with 2 mirrors sending signals using Morse alphabet or whatever else is way better because the information arrives almost instantly with the speed of the light. And this is the difference between bandwidth and latency. We increased bandwidth tremendously while latency stayed more or less flat. So what is this latency of DRAM? If we have a DRAM cell, something that is represented right now on the screen, we have 3 buses: data bus, address bus, and control bus, and some rows, some cells. The rows will contain actual data. The address bus and control bus will tell us from where to read the data and what we should do. Should we read or should we write the data? And data bus will be there to exchange actual data. So on address bus, I will tell what to read. Control bus will tell, yes, please read the data, and then data bus will move the data from one place to another. When it comes to DRAM, it's basically a huge set of transistors, and transistors needs voltage and current to operate. So I must activate one of these rows, I must pre-charge it so that I can read data. And now on address bus I am pointing to that activated row. then the data from that activated row will be pushed to the data bus. And this 14 nanosecond latency that we have seen earlier on the graph is related to that latency. This is the best case scenario. In case the row was not activated beforehand, we must find the inactive row, activate it, and it will add more latency end to end. But this is just DRAM internal latency. In computer system, let's take modern PC, we'll have few other pieces between DRAM die and actual CPU core. There will be some DRAM controller and there will be some bus between DRAM controller and CPU core. And this end-to-end latency can easily be on level of 50 to 100 nanoseconds in modern PC, something that you can have at your home. But is 50 nanoseconds really a lot? Let's put that into perspective. This 50 light blue boxes are representing 50 nanoseconds. Our reference is the end-to-end latency in the system. And it can be compared to one clock cycle. It will also take 50 nanoseconds, provided that we are talking about something like 8080 CPU clocked at 2 megahertz. If we will be talking about something modern but modest that is clocked at 1 gigahertz, then one clock cycle takes 1 nanosecond only. And if we are talking about top shelf products, then we can talk about 5 gigahertz clock rate, and then one clock cycle is only 0.2 nanoseconds. But for human being, nanoseconds are not something native. For us, milliseconds is the level that makes difference between champion in the sprint and somebody who takes second place. Nanosecond is few degrees lower unit. So is 0.2 and 50 nanosecond that much difference? Well, we need to look at it and scale it to something that we can understand better. And we are using usually something like seconds and minutes. And here I have a story for you, because I was working on that very presentation. I was getting into focus, I was in my comfort zone, I was working on the slides, and usually when I was looking for some good way to represent something, I would forget about whole world. But I had my mug of tea, and from now on then I took a sip, and at one moment I had this brilliant idea. In a heartbeat, I looked in the mug and there is nothing in the mug. And now I have to go to my kitchen, put the water, wait about 5 minutes, make the tea and go back. And that's the same difference. It took me one heartbeat, 1 second to just realize I'm out of tea. And then I had to go there, frustrated that I have no tea, go to my kitchen, boil that water, wait there, stall for 5 minutes, make the tea and go back. So it was frustrating for me, and CPU is not getting frustrated, but it will stall as well. It will do nothing for all the time. For 250 CPU cycles, it will have nothing to do. So that's the difference. For CPU, it's 0.2 versus 50 nanoseconds. For us, it's 1 heartbeat versus boiling 1 liter of water. And what could I have done to avoid my issue? I could have had huge jug of pre-made tea on my desk and just fill it, mark a low water mark on the jug. If it goes below, let's make a little bit more. I could have done it proactively so I wouldn't stall ever. And even if I would fail that because I was too focused to even realize that I am going below the line, the probability of that would be way lower. And this is exactly what CPU caches are about. We have the end-to-end latency of 50 to 100 nanoseconds, but we are putting a pile of memory right next to the CPU core, and this will be serving as the jug of memory. Of course, CPU cache cannot magically remove the latency. It's there. The die is not changed, the DRAM controller is not changed, the buses are not changed. So that latency will stay on more or less the same level. But for CPU, the relative latency will be way lower. It will be around 1 clock cycle or few, but no longer 50 to 100 nanoseconds. So this is what CPU caches are about. It's no magic. They will not remove latency. They will hide it. Now, if we have that cache, we have some kind of memory hierarchy. We'll have one cache next to the CPU core, it will be L1. Then we'll have next levels, L2, L3, RAM, maybe swap space on the hard drive, and so on and so on. We can see all that big hierarchy of memory as next level caches, because RAM is basically a kind of cache of persistent data or data that we have downloaded from the network or whatever else. What is important is the relative sizes of these memories. The sizes of the blocks L1, L2, and L3 are up to scale and up to actual figures that you could have found in a personal computer CPU that you can just go to shop and buy. So L1 cache will be very small, it will be around 64 kilobytes. Then L2 cache will be quite bigger, but still it will be kilobytes. L3 cache will be quite big, it can be around 8, 16 megabytes, but it will be shared between multiple CPU cores. And then RAM is not up to scale. The size of the RAM depicted here is 64 megabytes. It's nothing even close if we are talking about modern PCs. But even if we take into account this small size of RAM, the size of L1 is negligible compared to it. So that's why we cannot treat the cache as a free lunch. It's not that we can load any data next to CPU and it will magically improve the system. We need to organize the data, organize our algorithms so that we make it possible for the CPU, for the branch predictors, prefetchers to fill that small cache with the relevant data that we'll need in next clock cycles. And the simpler the algorithms, the simpler the data structures, the less space they occupy, the better benefits the cache will provide. One thing that is related to that fact that we have different sizes of memories on each level is that we will have to map it somehow. I have 512 kilobytes of L2 cache and I have 64 kilobytes of L1 cache. And now the question is, how do I map the data? If I want to move something from L2 to L1, where should I put it? What data from L1 should be evicted? What data from L2 should be put there? So this is called associativity of memory, associativity of caches. And there are a few different solutions for that. I'm going to show you two, direct mapping and set associative mapping on an example of two-way associative mapping. What is important when it comes to this mapping function is that it must be very fast, die size, and power efficient. The reason the caches are small is also that they are costly and they are occupying some space on the die, so there is a trade-off. We either utilize the transistors for CPU core or we'll put these transistors into CPU cache. So we are either making one less performant or the other. So we must take care about how big area we are going to take and how much power we are going to use, because we are also power limited. The simplest way to map the memory between two different memories of different sizes is direct mapping. As the name suggests, we'll basically take address of the memory cell in the higher level cache, do a modulo calculation by the number of rows in the lower level cache, and we'll be mapping it one to one. So 0th cell will go to 0th cell, first one will go to first one, second to second, third to third. It's kind of obvious. Then, if we overlap, we'll go from 0 again. So 4 will go to 0, 5 will go to 1, and so on. This is very simple. And the consequence of this simplicity is that it will be fast, because there will be very little number of transistors to do that, and it will be die size and power efficient for the same reason. Will occupy very little space. The function is so simple that it can be realized using very little area of the die and very little power. What is also very good about this kind of mapping of memory between different levels is that it will have optimal sequence traversal. So in best case, it provides optimal solution, because if I will be going by the cells in a sequence 0, 1, 2, 3, 4, 5, 6, 7, 8, then I am loading all that data to the lower level cache. There is no conflict. Whenever CPU is done reading the values, the data in the 0th cell, then I can start immediately prefetching data that is in 4th cell and keep CPU busy with data in next ones. So I have a lot of time to preload data, I have a lot of data to still process while I am preloading, optimal case for the best case scenario. The problem is that if I would be jumping each and every nth line, so in this case every fourth line, then they always will end up in the 0th cell in lower level cache. That means that every time I am trying to preload data, the CPU will conclude, okay, I have nowhere to load that data. It will finish doing the operation, then it will turn out that there is no data in a cache. It must be loaded either from higher level cache or from RAM. And in this case, this cache failed to hide the latency before the CPU. So solution for that is to organize the cache a little bit differently. We'll be talking about something called set associative mapping. Now, the caches are of the same size, but we have organized the lower level cache in a little bit different way. These 4 cells we had were organized in 2 sets, 2 ways each. I could have organized it also in 1 set, 4-way each. So there can be higher number of ways, but the concepts behind that will be exactly the same. So let's explain the 2-way mapping because it's simple to depict on the picture. So first of all, we'll work as in case of direct mapping. It's simple, we just take modulo 2 because number of sets is 2 in that example, and the cells will be mapped directly. So 0th will go to 0th set, 1 will go to first set, and so on and so on. But now I have another complication. I need to choose inside of the set, I have 2 ways. And I need to decide, should I put data here or should I put data here? And this is not obvious, so I need some kind of rule what data to evict from cache, remove from cache, and replace with new data. And frequently used solution for that is to evict the last recently used data. So I will have some comparator that will check, okay, this was last recently used, this was used further in time, I am evicting this data and putting new data here. And I will do it for each and every set and for each and every row in the higher level cache. The consequence of that is obviously that it is a little bit more complex than the direct mapping because I have to have these comparators that are checking what was last recently used. I need to select where to put the data, and the bigger number of ways, the more complicated the subsystem becomes, because I have to do that in as little number of CPU cycles as possible. I am here to reduce latency, not to increase it, so I must be doing all that in parallel. So I will be consuming a little bit more number of transistors, a little bit more die area, a little bit more power. The good news is that this kind of cache will reduce the cache misses by about 15%. And now I can invest that 15% either in expanding the performance of the cache or by shrinking the cache, keep the same performance but utilize less size of the die. And last but not least is this cache will help you with your parallel algorithms. If you have 2 CPU cores working in parallel and having 2-way associative cache, then you will not have CPU stalls because the 2 threads will be trying to address the same cache. Even if they will be hitting exactly same set, there are always 2 ways to put the data. There are 2 cores to put the data. And even if one core just load the data here, then this is less recently used. So second core will load data here, and so on and so on. They will be replacing their own data, but they will never clash. They will never stall because the other cache is trying to read the same data. So now it's important, if you have shared cache, to realize how many CPU cores you have and how many ways of associativity you have. If the number is equal, you are lucky because you will not run into issues of clashing over the same cache lines. In case you have less ways of associativity in the cache than the number of CPUs, you might have problem, and then we will need to proactively take care so that we are not addressing the same cache lines at the same time by different CPUs. But I have used a name of cache line, and it could have been thought that if I have a cache, it has 64 kilobytes, then I can address each of these bytes separately. And this is not true. In general, I do not have this kind of flexibility. There is something called cache line. It's another hardware physical property of the cache, and the cache line will always have fixed length for that given CPU. It cannot change. It might be 32 bytes, it might be 64 bytes. Between different CPUs you will have different sizes, but this one, it's fixed. Now the cache is not really a set of addressable bytes, but it's a set of cache lines. This means that if I have a memory in the RAM and I need to load it, I have to take care so that it's aligned to the cache line. I cannot load this kind of data in one cache line. Even the size matches, it's not aligned to the boundary of the cache line, so it will actually, in this case, occupy 4 of them, not 2. The size is equal to 2 of them, but the alignment makes it skewed, and it unfortunately hits 4 lines. I cannot offset it so it starts. I can do it if I take into account the memory alignment in application. But if I align the data in application, then the problem disappears. I will read the data at the beginning of the cache line, it will hit the cache line, and it will fill one cache line, and so on, and so on. So this is related to the alignment of data in application. So alignment will then have some consequences. I can under-align types, so I can have a structure of 4 bytes and force compiler to align it to 2 bytes. But then what can happen, because OS will be able to allocate the data anywhere in the memory where the address is divisible by 2 in that example, that I will have this data occupy RAM in this way. And I will lose a little bit of space at the beginning of the cache line and at the end of the cache line, and I expose myself to an issue called false sharing. False sharing because I will have some irrelevant data in the same cache line, and that irrelevant data might cause other CPU to try to hit the same cache line, and whole benefits of caches might be void. If I would align this data structure properly to 4 bytes, I can fill the cache line and it will always start at the boundary of memory divisible by 4, and it can fill the whole cache line. There is no chance I will leave a room where I couldn't fit it, but it still can happen that the data will be offset. So the address must be divisible by 4, but it doesn't mean that I cannot offset the data. And if for some reason it's important that this data must be always accessible at the same time for the CPU, for example, we are talking about quaternion that is represented by 4 integers for some reason, then what I need to do is to put the data together and ask my compiler directly, please align this data structure to 32 bytes, and then it will occupy that cache line always. So if I want to have the data in one place in memory, I have to align it to that boundary. So caches and cache lines will also have write consequences. If I have the data, it is already perfectly aligned, and I already took care so that the number of ways of associativity is equal to the number of CPUs or higher. There is no problem with parallel stalls and so on. There will be still one small thing that can totally ruin our parallel algorithm. Because I have the data in one cache line, but different CPUs, different caches cannot work on the level of single byte. So even if I am replacing just one piece of that cache that is irrelevant to other CPUs, then this whole cache line will get invalidated. And if it's getting invalidated, the CPU cache coherence process must take place. Other CPUs will be informed, hey, this line, do not use it. It's right now invalidated. I have written something to it, but whatever you have in your cache, forget it. This cache must be evicted, and we need to read it back. So there is a difference. In theory, if you have a sequence of integers, you could have traverse it and double each value with 2 threads in 2 ways. Either going one by one, so first would take odd indices, second would take even indices, or you can just have that, put some boundary in the middle, and first thread will take first half, second thread will take second half. In theory, they should perform the same way. There are two CPUs. There is the same amount of work for each of them. In practice, because of this invalidation and because of vectorization, the version where we are going odd even indices for two different CPU cores will not perform well. And now we have some time for an example to show where taking that data, where taking this all into consideration actually helped. So I had been working on a project lately with my colleagues, and we had a simple data structure, a simple database, where we had some kind of type, some kind of name, some kind of pointer to a parent of the same data, and some kind of parameters, a map of parameters. This type, you can think about it as entries in some kind of database that are depicting, for example, units in a game. Let's say it's a football, soccer game, so the type will tell us, okay, this entry is a goalie, this entry is a defendant, this is an agent, this is a manager, this is coach, and so on. And name, obviously, it's a name of that person, of that entity. Then parent, it might point, for example, for each and every player to their coach or to their goalie, whatever else. And then there is map of parameters. They are not interpreted directly here. It can be age, it can be number on a jersey, whatever. And the task is quite simple. We must find all units, all entities with the same type. How to do that? The simplest solution would be to just put all that data in one data structure, sort that data structure using the integer type as our key to that data structure, and then use equal range to find that value in the memory. Very simple solution. How it will perform, we'll see, but it's important to understand what is the consequence when it comes to caches here. Because if we take care about cache, this kind of data structure for this algorithm is something very wasteful. I have this type at the very beginning of the cache line, the light blue color, and the rest of the cache line is some padding, the name, the parent pointer, and the parameters map data structure, but in one cache line I have just one type. So when I am traversing this vector, when I am trying to find it, I am checking one value in each cache line, and then I am removing all the data because it's not relevant for the algorithm. On the other hand, what we could have done, we could have simply stopped overthinking and over-engineering things and use standard library. Either standard library literally or boost. There are different solutions for that. So let's just evict the type from the data structure and make it a key into boost flat map, map, or unordered map. Of course, since the types can be repeated multiple times, this will be the multi-versions of these data structures, and we'll be using equal range for that. And now the question is, how do you think which of these solutions was most performant? If you think that naive C solution with putting everything into the same data structure is the best one, raise your hand. Okay, there is one person who thinks so. Thank you very much. Then flat map. Who thinks flat map will be the best? There are few persons over the room thinking that this will be the greatest solution here, but still it's small percent of you. Then when it comes to multi-map, who thinks multi-map will be the best for that problem? There are few persons again. And last but not least, unordered map. Who thinks this will be the perfect solution? Okay, so probably the biggest number of people, but I conclude that most of you didn't have an opinion. Who didn't have an opinion? Raise your hand, please. Yes, most of you didn't have an opinion, and it's fine, because making guesses is not always the best thing. What is important is measurement. You never should blindly optimize an optimization. Premature optimization is a wrong thing, so if you're uncertain, it's good, just measure it. And I did these measurements, and these are the results. I have run all these algorithms on one of the computers I have. It has a little bit dated CPU, 12 gigabytes of RAM, DDR3 still, and I have used Clang 8.0.1. And I don't know if this is very well legible in the last rows, so I will read for you the legend. The red color is flat map, the green color is map, the blue color is this naive C solution, and this purple color is unordered map. And what we can see is that at the very beginning, unordered map was unbeatable. But later on, when the number of bins grew, unfortunately, the size of the data structure grew as well, and it didn't fit memory well, and the execution time also skyrocketed. But what is important for the other algorithms is that there is no clear winner here. They are performing more or less similar. There are some differences at the beginning. At the end, the situation changes. So there is no one thing that works clearly better than the others. And when we will take a look at the very end of the graph, so here we can see that for some reason flat map and map skyrocketed. And the reason for that is that my computer has run out of RAM memory and it started swapping. It started using hard drive, and this is the result. So the algorithm is still good, but the fact that I have to use swap and not cache that data in RAM makes it so slow at the end. The I was just going I was just going to explain that, so I will answer that immediately. Otherwise, I would ask you to keep it at the end. So this naive solution is a little bit better because it doesn't allocate any additional data structures for bookkeeping, like sizes and so on. It uses a little bit less data, and thanks to that, it doesn't have to evict any page from the memory to the swap. So it's not much better. When it comes to map, yes, map consumes significantly more memory than this naive solution. Flat map should be consuming more or less similar, but still this naive solution doesn't have any boilerplate around it, and it's very, very simple. Yes, from that graph, the C solution is better. But if we would try to go a little bit further, they would again all skyrocket and be more or less the same. So this is just one data point. But if we were looking for this range of values, then this is sweet spot for this C solution. But can we do better? And of course, if I am asking this kind of suggestive question, then yes, we can do better. And I know that we can do better because we did better. And this is the solution that we used. Or it's not yet it, but this is different CPU, but the results are more or less the same, but this time I didn't run out of swap. But the results are more or less similar. Flatmap here performs a little bit better than previously. But can we do better? Yes, and this is the proposal. So we are evicting the type, moving it to separate vector of types, and then using equal range just on that vector. This is a little bit more complex when it comes to managing that memory, because now I have two vectors that I have to keep aligned. If I'm moving some type or some entry, then I have to take care about other vectors, so I have kind of bilinear structure that I have to zip together. But now, when I have all that in memory, I have all the types filling cache lines one after another. And now, even if I am not able to predict exactly that this data will land in that very byte, I can predict more or less in which cache line that this will be. So I have maximized the probability of finding right data in the memory that I already have in the CPU cache, or that memory that I can prefetch easily. Algorithm is very simple. It's just division and some additions, so it's easy to predict what data will be loaded next. And how that one perform? This is this one added at the very bottom blue line, and we can clearly see that in the whole range it performs better. And the reason it's flat at the beginning and starts rising later on is because it uses the L2 cache of the CPU way better. This CPU doesn't have any L3 cache, this is more or less the size of its L2 cache. So L2 cache was filled with the data and serving the CPU instantly. When we ran out of that L2 cache, yes, it started rising. The number of objects here is given in logarithmic scale. Algorithm is having logarithmic complexity, so this is why we have some kind of flat linear growth for each and every of these algorithms. And when we'll go to the next CPU, well, it works more or less the same. It's again way faster. This CPU has way more caches, that's why the good performance ends here, but later on it is still better than the other solutions. I understand that if you know how Boost Flatmap works, you would like to ask right now why Boost Flatmap didn't deliver, because in theory it's implementing the very same solution, and the answer is I have no idea. I was not able to pinpoint it to a very specific line in Boost Flatmap. If I would be, I would issue a patch. So far I didn't resolve that one. So, is the result good? Maybe not the best one in the world, but I think it's not bad. Okay, but I told you all that things, and now you have to believe me that this was better because of caches. And I didn't prove to you so far that caches are there, and that this caches is what makes the magic. So let's take a look at what happens here if we run a profiler. First, number of instructions that were used by each and every algorithm. The lower, the better. The colors are the same. First, we have flat map, the red one. Then we have map, the greenish one. Then we have naive solution, the C solution, the green one. Optimized solution, blue one. And pink, magenta, the unordered map. What's very interesting on that diagram is that the less is better. But we said that optimized solution was best. But from that graph, we can clearly see that map-based solution makes a lot less instructions. There is 25% gap between number of instructions in case of map-based solution and in case of the solution called the optimized one. So what is the reason for that? And now I can tell you finally, and I have some argument to convince you, that this is because of caches. If we take a look how all these algorithms are using caches, then we have some different situation. These are representing L1 misses and L1 uses by each of these algorithms. And now situation is dramatically different. If we take a look at map, it's using more or less twice as many cache, and it's also having twice as many misses as the optimized solution. Cache was purged, it was empty before the execution, so any data that had to be loaded must have been accounted either in L1 uses and L1 misses, and there is no room for any cheating. It is not so that cache was prefilled with right data for optimized solution and it wasn't prefilled with data for map. It was just empty. Everything got dropped and then algorithm was run. And here we can see that map solution didn't deliver because of the cache misses. Next thing is last level cache misses. And last level cache is in this case L3 cache. I have run it on a CPU with L3, and we can see that again the pattern repeats. Here the differences between optimized solution, naive solution and flat map solution are not that different, but there we had higher number of instructions attributing additionally to the speed, or rather additional time needed for processing the data. In case of map, we have again almost twice many last level cache misses, and that contributes to that added time, added latency, and therefore worse performance. Even in theory, all these algorithms were logarithmic, but the unordered map was supposed to be to have constant access time. All of them were logarithmic. All of them were, in terms of computational complexity, optimal ones for the solution, but because of how they utilize CPU cache, they didn't work exactly the same way. And the conclusion from that is that if you take care about hardware you have, if you know what algorithms you need, you know your data structures, if you measure it all, you can deliver something that you wouldn't be able to deliver always. I will not convince you that every time you are doing something in your work, writing a regular expression to process data, you need to take care about CPU caches. No, it's not that. What I want to convince you is that if you ever feel lost, you have no idea how to speed things up anymore, but you would like to, or you have to speed it up, think about your hardware. Think about, am I using CPU caches in an optimal way? And then you have now some tools. You now understand the organization of the caches, so you can check if I am really targeting the cache I am using. And you also understand the latency. You understand the fact that in case I miss the data, it's not in cache, I will have to pay this 50 nanoseconds more for accessing the data. And I hope one day you will make good use out of this knowledge. Thank you very much. I'm Kamil Witecki. I hope you enjoyed the talk. If you feel you want to go deeper, stay in this room later on, and there will be more coming. If you want to have questions, we have time for that now. If you feel you don't want to ask now, or you would like to contact me later on, there is my email address on the screen, kamil.witecki@nokia.com. Feel free to get in touch with one another. Thank you very much again.
Thank you very much, Kamil, for excellent talk. Now we have time for some questions. Yes.
I feel a little bit discomfort when it comes to this first bar graph. If we can come back. Bar, with these bars. You mentioned
This?
No. Next.
This?
Yeah, bar. You mentioned here about the instructions, but in my opinion, the instruction cache has nothing to do with all this algorithm.
Oh, I was not mentioning the instruction cache.
Yeah, but if these are instructions that, in my opinion, they do not, let's say, influence how the algorithm works. It's all about the data cache in this case.
Exactly. So this is the number of instructions that algorithm executed. In theory, map-based solution executed less number of instructions. So in theory, it used the less number of steps to get the job done. But because it didn't use cache in the right way, the latencies for each and every
data
of this
cache.
Yes.
Yeah, but the whole algorithm could, let's say, fit two
could
instruction cache, and instruction
Yes.
cache has nothing to do with.
That's true. So this is
Okay.
just the number of instructions that were executed, not how they were
So
cached.
in my opinion, those, let's say, bars are, let's say, meaningless when it comes to the instructions, because in all cases, all instructions will fit to the instruction cache.
That's true. What I am saying is that frequently people are optimizing software taking into account how many instructions were executed. Because the less instructions my application is executing, in theory it uses CPU less, so it should have used less CPU cycles for that.
Okay, I agree, but not to this,
Yes.
let's say,
Yes,
scenario.
it has nothing to do with the cache, and this shows that number of instructions is not enough to really judge how well algorithm will perform.
Okay, thanks.
Hi, I have a question about this graph actually, about an ordered map result. And do you investigate why you get such horrible results? The case of instructions about.
If you could repeat, please, because I was not able to understand you right. There was some noise. Please repeat.
Okay, so do you hear me right now?
Yes, yes. Or maybe I will just approach you, ask directly, and I will repeat it.
Why there are 95 times more instructions than on an ordered map? Have you investigated this? Because it's like a lot.
That's a good question. The question is, in case of unordered map, why the number of instructions skyrocketed and it is few orders of magnitude higher than in case of other solutions, and if I have analyzed that. The truth is, I haven't, and this is because I knew that the area I have to be working on is more or less here at the end of that graph, and already here this unordered map-based solution was not providing very good results, and even at the beginning, where we have very little data, these optimized solutions turn out to be better, so I didn't pursue further checking the unordered map and why that didn't provide. But this is valid question.
We want to optimize our code for different CPUs with different size of cache line, which alignment we should use? The smaller or?
It depends on specific CPU. If you are targeting very specific CPU because you are working in an embedded software development,
Yeah.
then you know exactly that, okay, I am working with, I don't know, Octavian Cavium C and something, and then you know it has 32 bytes, use 32 bytes alignment. The problem starts when you have to make a solution that will address any cache there is. For example, you are working in a company that will be making word product software that will be running on PCs. Somebody can have dated CPU, as I had in one of my computers, that will have no L3, that might have different L1. Somebody will have modern CPU, somebody will be working in HEDT platform. Then you have no idea, and you actually can do very little about it. You either will have some trade-off, and you will need to select, okay, I want to target it for these processors because these are the processors that are less performant and optimize for these ones, or use something that can adapt to specific CPUs using, for example, so-called cache oblivious algorithms. There are solutions like that. This is beyond this very high-level overview, but I believe that in the talks that will take place in this room later on, there will be topic of cache oblivious algorithms, and Yossi is nodding his head, so now I am sure there will be some answers for you.
Okay, thank you.
You're welcome.
Hi. So a common problem usually when with the STL and other standard containers is that we all share the pain of the performance sometime, but what is missing is usually the benchmarks to actually improve it. So the question is, do you have a benchmark? Do you plan on publishing whatever you use to generate those graphs so we can actually try to pinpoint if it's an implementation issue in the STL or something?
Oh, that's a good question. I was not thinking, should I publish it or shouldn't I publish it? The results were done in my private time, so I do not have any reason not to publish it. Okay, I will publish it in GitHub, and you will get it next to the presentation on the CodeDive page.
Thank you very much.
Hi, Kamil. You told that the cache was emptied before any of these algorithms were executed. How to empty the cache in C++? Or have you used any assembler instructions for that?
Another excellent question. In that case, you can use directly assembler instructions of the CPU. There might be some intrinsics, but in that case, I was using Valgrind with some tool called ColdGrind. And it provides you a header that lets you to start, stop measurements, and you can, when you tell it to start measurements, it prepares the environment for you. So I have used what ColdGrind provides.
Okay, so you can even preload some data to the cache with this.
If you preload the data and you tell Valgrind start measurements now, it will empty everything.
Okay, thank you.
Hello. Did you check on different platforms? Some Intel, maybe some Xeon, something more stronger?
That's a good question. I didn't have access privately to this kind of platforms, but the differences between modern AMD CPUs, I'm not talking about the dated one, but the new one, and the newest Intels are no longer that huge. So the sizes of the caches are a little bit different. Intel is a little bit better in access to the DRAM, but These results are more or less representative for both of them. I had no access to any HEDT or Xeon or any server processor what could have made a difference.
Thank you for the talk. The question is, I guess this is all one-threaded application.
That's true.
Have you tried with multiple threads, multiple cores used? That's first question. The second question is, what about, because your solution is basically put each keys into one array. All keys into one array.
Mhm.
So how does this solution influence write operation, not read?
That's a very good question again. In that case, it was all about reading. The data was always loaded once, and we had to execute thousands, hundreds of thousands consistency checks after loading the data. So we load the data once at the startup, and then we have to run huge number of consistency checks on it. And we never write the data after we loaded it. So I didn't measure writes because simply for that problem I had to solve, it was irrelevant. When it comes to multi-threaded accesses, I didn't want to have just that algorithm, so finding done in a multi-threaded way, because on a higher level, when executing these consistency rules were executed in parallel. And this all these data structures didn't impose additional issues when it comes to CPU usage or stalls. So we got more or less n times improvement. It was a little bit better because of accounting, but it was in promised range when it comes to number of CPUs and number of times the results improved.